Okay, welcome, Mike, and hopefully others will show up too. This is the week 9 webinar. We're getting through a lot of the course now, and the plan today is to talk about what's called chi-square distributions. And the idea is, it's something we have not yet done in this class at all. We have completely focused on survey questions where the answer is either quantitative, like a number answer, or the answer is a yes/no answer. Hi, Pooja, thanks for coming. So now there's a couple of you, which is good. So we're gonna be doing the chi-square distribution. I wanna remind you, because it's always good to remember these kind of things, if you look at your syllabus, you will see that project 2 is due by March 15th. I know that seems like a long time from now, but you'll see time flies fast. And let you know, and I apologize, but I'm gonna be in interviews all day on March 12th and 13th, and I'm gonna be at a Pi Day conference on March 14th. So the few days before, I'm not gonna be around much. I might be able to check my email once in a while. I'm not gonna be able to spend, hours working at stuff. So I'll be able to answer quick questions, but not big, long things. So I apologize for that, but I'm on an interview committee, and hiring a really important person, hiring a really good person is really important to the college. You hire the wrong person and life sucks for everyone. So I'm gonna be in the interview committee next week. So just to let you know, that's happening. The good news is we got a message from the president of our college that there's a not that small chance that our college is going to close down. And the good news is, if we do close down, we're going to go to only online classes. And any guess on why we might be closing down? And hopefully this doesn't happen, but
it's always budget.
It's not budget.
No.
But it was a good guess. No, the coronavirus. So it's reaching through, and I don't know how, I know you're not all from Tahoe, but we are the tourist destination in California. And we get people from all over the world. And that's a bit scary when it comes to the virus. So if we get the virus, then we close down. But the good news is, online classes don't close down. So that's the good news. So again, you'll hear about it if it happens, but it won't affect you guys at all, which is good. So hopefully it doesn't happen, but if any place has to deal with it, it's Tahoe, actually, if you think about it. I don't know if you've thought about that, but we are the place that has the kind of the biggest variety of people from all over the world come here. And that pretty much makes us a big target. So hopefully it doesn't happen. So, and if it does, it doesn't matter, we're in online class. Okay, so what happens, happens. So let me ask you, are there any questions about anything before I move on to chi-squared, and we're gonna do a current events. And welcome, Calvin. Any questions about anything?
The only thing I have questions about is the project.
Yeah, what is it? What's your question?
Basically, I'm having trouble just coming up with a good, the question to start with.
Is it the question or the hypothesis you're having trouble with?
The hypothesis.
Okay, because once you have a hypothesis, it's usually easy to come up with a question. We haven't seen, actually I haven't seen any real ones that would work that got posted yet. But I've been doing this for many, many years, and there's lots of hypotheses that could work. Maybe I'll give you some examples, things that you probably wouldn't do. But they're examples that other people have done. So remember, you have to hypothesize about the difference between two population means. So for example, I had a group, and this was kind of raised my heart. I don't know if you remember, I teach math, but the other thing I taught, anyone remember? Totally different, it's karate. And we actually had a karate instructor, and he wanted to find out if stretching actually improved flexibility. So if stretching for 5 minutes will increase the angle at which you can take your legs and do that with your legs. Okay, do the old splits. So he just measured the two. Okay, so that was one. Again, you don't have to do a survey. That wasn't a survey. You can also collect data. And that could be from a business, for example. Maybe I've had students that worked in a business and they wanted to find out if people spend more on the weekends. Does that make sense? So looked at receipts on Saturday and Sunday versus looking at receipts Monday through Friday, and did that hypothesis. I don't know if that helps at all. Or
yeah, I think it does.
Lost. But the important thing is you have to have a collection of data, and the data have to be comparison data. So you should have data so that you have either before and after data, or it could be this group versus this other group data. And the data should be a bunch of numbers. Things like receipts, how much people spent, or what angle people can flex, or whatever it might be. And you're comparing two things that are comparable. Does that help a little, or is you still lost?
I'm still lost, but it helps. It helps a lot, actually.
Yeah, so the idea is come up with, imagine two data sets that you're going to compare. Okay, and it could be two different types of people. It could be two different days. It could be the same person with two different features, like before and after on their stretching or something like that. There's lots and lots of different things people can do. Something that my other class is doing, you guys have to identify a client. They actually have a client, and they are looking at real estate differences. So they're looking at this year's home prices versus home prices from last year. Does that make sense? And wanting to find out if prices have gone up in our area. So hopefully that helps. Again, I can go on and on with more and more examples, but those, I don't want to tell you have to do this one, but I want to let you know that that's what they look like. Should be two sets of data at which you're comparing. And again, sometimes you do a survey, sometimes you just collect the data off on the internet. Depends what you're doing. If you can get the entire population, it's not okay. So that's one thing to look at. So for example, don't look at, if you looked at the Astros versus the Dodgers and saw who scored more runs last year. Well, the thing is, it's very easy to find the 162 games and find out how many runs they scored and get the whole population. So it has to be something you can't get a population of. Any questions on that? Okay, so let's move on. Let me ask you, what's the big thing happening today? And if you've looked at the news and you've seen it.
Election.
Yeah, I don't know if you can see.
All the primaries.
There's I don't know if you can see, do you see my lapel? I voted. So let's take a look. So I got a current event to look at. Just a minute. Yeah, the big thing is the elections. So let's take a look. So CNN polls. Bernie Sanders holds the leads in California and Texas ahead of the critical Super Tuesday vote. Okay, so what I'm interested in is thinking about the survey question. So in California, what do you think they asked everyone? What was the survey question?
Which candidate are you voting for?
Right. Yeah, what candidate are you voting for? And you're not going to say 73. You're not going to say yes. Is that clear? You're going to say Biden or Sanders or Bloomberg, right? Or Warren. Those are the four main ones. Is that clear? So this is the first time in this class we've really dealt with analyzing data where the answer's a word, a name in this case. And the test we're going to be looking at is to see if they're all the same or not. Okay, it says CNN saying Bernie hold the lead, but how do we know that? Okay, so let's take a look. So it says in California, results suggest the same four contenders hold the most support, though Sanders stands well ahead of the other three contending for second place. Sanders holds 35% support, Warren at 14%, Biden at 13%, and Bloomberg at 12%. Okay, do you believe that? That's the exact percents for California?
No.
Yeah, definitely we know. Hopefully you've learned enough in this class to know that we don't know about all of California. But what we can conclude is that they took a survey. Okay, and they give a sample size, but I'm going to let you know it's a little different than you think. So if we look at the sample size in California, it tells you over here somewhere, 1,000 something if I remember right. Yep, 1,197. But I'm only going to include the people that are said one of these four, because there's other people that are running, okay? Or we're running and people have already voted, like myself. I voted a while ago, and I could have voted for one of the people that is no longer running. So what I'm going to do is I'm going to write out a hypothesis test for this and talk about what's going on, something you can do with qualitative data. So let's go to here. So what we're going to do is we're going to have a hypothesis. Hopefully you're used to that by now. You better be. And we're going to have H naught. And I want to let you know, this is a big warning, is that for chapter 11, H naught and H1 are done in words. Okay, do you remember chapter 9 and 10? We didn't do these with words, we did these with symbols. So if on the final exam, if there's something coming from chapter 9 and 10, don't use words. Got it? Is that clear? So this is a warning before I start typing. In chapter 11, we're going to use words, but that doesn't mean that now we can go words with everything, just this chapter. So H naught is, well, the idea is maybe all the candidates are the same. So what we can say is the distribution of candidate choice is, now in math, in our class, if they're all the same, we had a word for that, a statistics word. What word did we use? Can you remember? We had a whole chapter on it, basically. Does that help? What word do we use if they're all the same? Median is the middle of the data, but it doesn't mean that you have a bunch of things that are all the same. Median is for quantitative data only, by the way. Okay, start with the U.
Uniform.
Uniform. Okay, any questions on that? So if they're all the same, then we call it uniform. And that would be H naught, is that we have a uniform distribution. So I want to let you know something. This is very important when we're doing this kind of hypothesis test. And I ask you to write H naught and H1. That word distribution must be there or you lose points. Got it? So for the final exam, you must have the word uniform. Must have the word distribution. Okay, H1 is really easy once you have H naught. And that is the distribution of candidate choice is not uniform. Any questions about H0 and H1? Okay, you're saying what is all the same? What's all the same is the distribution. So in particular, the percentage of people who are voting who like Warren, and the percentage of people who like Biden, and the percentage of people who like Sanders, and the percentage of people who like Bloomberg, all four of those are the same. Does that make sense, Pooja?
Yes.
And when they're all the same, we call that uniform. That was a word we used. Okay, so the next thing we're going to do is I'm going to draw a table. So let me make a table out of this. And what we're going to do is we're going to have a few things. I actually got to do a little more on the table. So our entries are going to be Sanders. I'll try sand. And then we're going to have Warren. How about war? And then we'll have Biden. Bid. And Bloomberg below. And then for the rows, what we're going to do is we're going to do the following. We're going to write observed, and it's going to use O for observed. That's standard. And expected. Any questions so far? Okay, now I'm not going to go back to the article, but I will tell you I did a little bit of math to figure out how many people said they liked Sanders, how many said they liked Warren, how many said they liked Biden, and how many said they liked Bloomberg. And what I got was 419 had Sanders as their first choice, 168 liked Warren, 156 liked Biden, and 145 liked Bloomberg. Any questions so far? Okay, now I will let you know the sample size was 888, it turns out. Okay, it did a little work actually for me to find the sample size, but trust me, that's what it was. So how do I find the expected value, expecteds? So expected means that if H0 is true, how many would we expect to like Sanders the most? Any thoughts on how I find how many people would we expect to like Sanders the most?
Find the percentage. So
what's that?
Find the percentage. So 419 divided by 888.
It's a good idea, but no. So the 419 is the observed. And you could do the expected before you even observed anything. Does that make sense? So if we know we're going to ask 888 people, and we want to say, what do we think? How many do you think are going to vote for each if it's uniform?
It would be even then. They would all be the same. So 888 divided by 4. So
exactly.
222.
888 divided by 4, which is 222. So the expected for each of these is going to be 222 because of the uniform assumption, or uniform null hypothesis, better word. Any questions on this? Okay, so the next thing we're going to do is we're going to decide what kind of test we're going to use. And what we've got here is we have one population, right? Population of California voters. And we want to find out if the distribution for their vote choice fits a given distribution uniform. When we want that, we call it goodness of fit, because it fits that distribution of uniform. So we're going to use a chi-squared goodness of fit test. Any questions on this? All right, now comes the good news or bad news. And it all depends on whether you're having a good day or not. And I can't tell you, I don't know. So let me ask you, Mike, Cullinan, and Bridget, do you have your calculator with you?
Yes.
So hopefully you all do. Okay, get your calculator out. Okay, it's very important you follow along, because we'll find out whether you have good news or bad news. And the bad news is not all calculators are the same, so you hope you have one of the good ones. So I'm going to share my calculator. And what I'm going to do is I am going to go to stat. This is the same for all calculators, by the way. Then I'm going to edit. I'm going to clear out L1. You're used to doing this, hopefully. I'm going to clear out L2. Then under L1, I'm going to put my observed numbers. That was 419, 168, 156, and 145. And then for L2, I'm going to put my expected. And those were all 222. Any questions so far? So hopefully you're following along and doing the same thing on your calculators. Okay, now the most important thing you do right now is cross your fingers and hope. So the next thing I do is I go to stat. Then I'm going to go to test. You're used to this. And then I'm going to go to the up arrow. Now take a look at your calculator and tell me, do you have this GOF?
Yes, I have it.
Then you have a lucky day. Pooja, do you have it?
Yeah.
Oh, good, good. Kalina, do you have it? Good, good. So we're all lucky. That's the good news. By the way, some of you are watching this in archive video. You may not be lucky. So if you're not lucky, there's two choices. One is if you live in Tahoe, come to my office during my office hour, and I have a calculator and I have a connector, and I can feed a program that I created in my calculator into your calculator using this connector. Okay? Calculators are old-fashioned. They don't hook to the internet. So literally you got to physically do this thing. Okay? If you can't come to Tahoe, then if you go to Canvas, you'll see there's a link to a video on how to do it, and you got to hit all the buttons perfectly, and you can make that happen. But at least the three of you, you don't have to worry about it, because you've got it. Okay, so then I'm going to go up, as you might guess, to that GOF. Hit enter. My observed is L1 and my expected is L2 because that's what I put in. DF. DF stands for degrees of freedom. And degrees of freedom are the number of possibilities minus 1. So in this case, we had Sanders, Warren, Biden, and Bloomberg. So what's the degrees of freedom?
3.
3. 4 minus 1. I hope you didn't get your calculator out to do that. You should know 4 minus 1 is 3. So the degrees of freedom is 3. And then it's very easy, you hit calculate. Okay, so to let you know the test statistic, this is not an X, it's a chi. Okay, that's a Greek letter. And its chi-squared is 234.2793 about. Okay, it's a very, very big chi-squared. Is the p-value 1.6426.7?
No.
No, remember the p-value can never be bigger than 1. Okay, that'll never happen. What is a p-value?
Uh, 49 decimal places on the other side of the 1.
Yeah, it's ridiculously close to 0. I like Pooja's answer, which is exaggerating the zeros. Do you see that? So what the conclusion is we get to reject H naught. And you should all know that when the p-value is small, you reject H naught and accept H1. Any questions on that? Okay, so now let's go and write out our conclusion. And that is, there is statistically significant evidence to conclude that and all we have to do is rewrite H1, distribution of candidate choice is not uniform. Any questions on that? Okay, does this say that more people like Sanders? What do you think? Yeah, it doesn't say that. All it says is the distribution is not uniform. Okay, if you want to be able to use statistics to say more people like Sanders, I'll let me know the bad news, and that is you need to take another statistics class, because that wouldn't be elementary statistics, that would be intermediate statistics. And then you use something called a two-key test, and that would work. You don't need to know that because it's not part of this class. But I do want to let you know that there are ways to continue on and investigate further after you find out that it's not uniform. Now, which is the one is more, which is the one is less? Does that make sense? But we don't know how to do that, and we're not going to learn how to do that in this class. All we're going to do is to learn whether or not the distribution is what you think it is. And that's as far as we're going to go for this test. Any questions at all on this idea? Any questions? Okay, so again, I want to emphasize the survey question was qualitative. Who are you going to vote for the Democratic primary? And the answer is a word, like Warren. It's not a number, it's not yes or no. So any questions on this idea of goodness of fit? Okay, I'm gonna erase this so I can do some other examples. I like to at least have one example that comes from today's news or recent news, and this is definitely today's news because the primary happened today. And I voted. I actually honestly voted a couple weeks ago, but I voted at least. Let me go and let's put a new one in. Okay, so here's the next question. A study was done to see if there's a difference in the distribution of cars for men and women. Of the 200 men surveyed, 70 owned a foreign car, 110 owned an American car, 20 did not own a car. Of the 300 women surveyed, 110 owned a foreign car, 158 owned an American car, and 32 did not own a car. Conduct the appropriate hypothesis test and provide your interpretations. So I want to ask you, what makes this question a lot different than the last one in terms of the data or the question? There's one major difference in terms of what we're doing. Any thoughts? The difference in sample size, not quite. Not quite the best way of wording it. Any thoughts? It's qualitative, but the last one was qualitative also. Right? The last one was qualitative because we said, who do you want to vote for president for the Democratic ticket? And that was qualitative. And this is also qualitative, right? What kind of car do you own? Sample population. I'm not sure what a sample population is. That's like a contradiction in words. Right? There's a sample and there's a population. Okay, so maybe I need to let you know. The big difference between this one and the last one is the last one, we had one sample. We had the sample of Californians that we asked the question of. Here we have two samples. Yeah, as Pooja says, there's two groups. There's a group of men and there's a group of women. And we're comparing the distribution of men to the distribution of women. Whereas the last one is we have this fixed distribution, uniform, and then we had a sample to find out if it was. So that makes it very different, and we're going to use a different tests. So let's write out, as you're used to hopefully by now, the null and alternative hypotheses. So H naught is the distributions of car type are the same for men and women. Notice this one's plural, distributions, because there's two distributions we're comparing with each other. And we don't know either of the distributions. H1 is exactly the same, except it's not going to be same, it's going to be different, or not the same. So the distribution of car type are not the same for men and women. Any questions on H naught and H1? So we're not trying to fit one distribution into something we know. We're comparing two distributions. So we can't use a goodness of fit test. So in this case, we have a different test. It's still going to be chi-squared. Today is chi-squared day, by the way. It's the chi-squared test for homogeneity. Is the test we're using. Any questions on that so far? Okay, and the chi-squared test for homogeneity is very important because it allows us to compare two different groups' qualitative answers. And that's what you use homogeneity test for. All right, so now we don't have an observed and an expected. Now we have two different observeds. Is that clear? We're still going to draw a table, but it's going to look pretty different than the last one. Okay. So what we're going to have is we're going to have the different card types. And the different card types, if we saw, there was foreign. I'll just call it F for foreign. Then we have American. How about A for American? And how about N for no car? Fan. Okay, and then we're going to have men and women. There we go. I think I'll just write WO because I don't have room. Okay, so for the men, the observed were 70, 110, and 20. And for the women, so I just noticed Pooja said, why is there no expected? Because we're not comparing it to a known distribution, so we don't know anything. We just have two groups for comparing. So whereas before we said, well, we're thinking it might be uniform. If we think it might be uniform, then we have an expectation because uniform has special numbers. Here it's just men versus women. Okay, so for the women, by the way, it was 110 and 158 and 32. Any questions on this? Okay, so the next step, you're used to this, is you go to your calculator. So the good news here, by the way, is that all calculators can do the homogeneity test. Good as a fit, only the newer ones can. So now I'm going to go to my calculator. And this is going to look very different than anything we've done before. In fact, we're hitting a button that you've never played with probably, and that is the matrix button. So second matrix. Then I'm going to go to edit and enter. And we have two rows, men and women. And we had three columns, foreign, American, and none. Hit enter, and that pops a matrix in there. And what I'm going to do is I'm going to put my numbers into the matrix. Any questions on this so far? Okay, so now let's put the numbers in. We had 70. And then we had 110. And then we had 20. And then for the next one, we had 110. And then we had 158. And then we had 32. By the way, you don't have to have the same number of men and women. That's not necessary. Oof, that just says 3 and it should be 32. That's much better. Any questions so far? Okay, so now I'm going to go to stat. I'm going to go to tests. Up arrow is much faster. And I'm going to go to the one that just says chi-squared test, the one that doesn't have the GOF. And that's the one we use for homogeneity. The observed is A, is fine. Expected is B. And then I calculate. Okay, what do you notice? What's the main takeaway here for these numbers? Hopefully we've done enough hypothesis tests to know.
Well, the p-value being at 0.8, you're going to fail to reject.
Yeah, the p-value is big. Okay, our chi-squared is small, 0.2658, and our p-value is giant, 0.88. So when the p-value is large, certainly larger than 0.05 or any alpha you'd use, then you fail to reject. So now let's write down the conclusion. And I may have to put it all over here. There is insufficient evidence to make a conclusion whether or not the, oh, I'm going to run out of room here. Distributions of car type are the same for men and women. Any questions on this? Notice that if we have a small p-value, then we say there is statistically significant evidence to show the distributions of car type are not the same for men and women. Okay, any questions on the test for homogeneity? Any questions? Okay, let's look at another problem. So let me select, get rid of this. Okay, so here's the newest question. Is there a relationship between the day of the week a person is born and the type of smartphone they own? What do you think? Do you think there's any relationship between the two? Like if you're if you were born on Thursday, maybe that makes you an iPhone user. Do you think that's true?
No, I don't think it's true.
No, probably not. I want to let you know I made up these numbers, but you could come up with it. Oh, Pooja, you think it's true? I made up these numbers, but you could do a study like this. Not for your project, by the way. The project's not on chapter 11. Okay. Table below shows the results of a study done. Do the hypothesis test. So here the table's already given for us. This is very different. How is this one different than the other two? It's 3, but even had it been 2, even if we just had iPhone and Android and didn't have any others, then it would still be different, actually. It has to do with, we want to find out if there was a relationship between the two instead of, are the distributions the same? Any questions on that? So it's the way we're looking at it is what changes. So this is a third test. It's the third test for this chapter. And this is called the chi-squared test. For independence. And that's the name of the test we're going to be using for this. So because of that, let's write down H0 and H1. H0 is that smartphone type and birthday are independent. Let you know if you're doing a test for independence, you must have the word independent in your H0. Or guess what will happen to you on the final?
Lose points.
Lose points. So don't lose points. So if you're doing a test for independence, I want to see that word independent. And H1, not high, H1 is something very similar. What's the opposite of the word independent?
Dependent.
Yeah. So very easy to copy and paste and get rid of the in. Smartphone type and birthday are dependent. Any questions so far? All right, what it turns out, and there's no way in the world I'm going to be able to explain this to you on the webinar, is that the mathematics behind the test for independence and the test for homogeneity is exactly the same. Okay, the ideas are different, but the math is the same. And because of that, we're going to do exactly the same thing on our calculator. So let's go ahead, go to new share, let's go to the calculator, and I'm going to go to second matrix. We're going to go to edit, enter. Now we had a 3 by 7. And now let's put all our numbers in. 75, oops, 75, and then 72, and then 68, 77, 70, 86, and 80. Okay, then we had for Android 120, 111, and then we had a 131, and then we had a 125, and then we had a 118, and a 124, and a 101. And then for the other, we had 45. Didn't read the 45. And then 52. And then 44. And then 50. 57. 46. And 52. Any questions at all on entering the data into this matrix? Okay, so the next thing I do is we go to stat, we go to tests, up arrow is much faster. And again, since the math is the same, we do exactly the same thing that we did in the last example. The difference is the wording. I hit enter, observed as A, expected as B, and we hit calculate. And what do you notice? What do you see?
The p-score at 0.69, we would fail to reject, so there's insufficient evidence to show that it's dependent.
Right, right. And by the way, are you surprised?
No.
No, no. I try to make, even though I make up the numbers, I try to make them realistic at least. And yeah, you would expect it to be insufficient evidence. I doubt that day of week has anything to do with the smartphone type you're born, but who knows, right? There are people who believe in astrology, for example. I'm not one of them because I've looked at the statistics and no. But, you know, who knows? So let's go and let's write down the conclusion. So let's do that. There is statistically insignificant evidence to make a conclusion about smartphone type and birthday being dependent. Okay, just a note, another way of saying this that you'll often see in literature is that we do not have enough evidence to say that smartphone type is a fact, or sorry, day of the week born is a factor in smartphone type. So sometimes they'll use that instead. It means exactly the same thing. Okay, in terms of the conclusion. But since it's the test for independence, I like to use word dependent. Any questions at all on this example? Okay, let's do another example. And I'm not going to do the whole example. Well, sorry, let me erase first. It's missed. Ah. Some weird stuff just happened. That's better. I'm not going to do the example. I'm just going to talk about it, and we're going to see if you guys can figure out what type it is. So let's go and copy and paste. Oh, that might be a little too small. Let's Control Z. Try again. That's better. Okay, so men and women statistics students were asked how much they agreed with moving from a calculator-based statistics class to a computer-based statistics class. The results are shown below. Conduct the appropriate hypothesis test, provide your interpretations. So I'm not going to do the whole problem. What I want to do is I want to see if you have an idea of what test you might want to use. That turns out to be the hardest part about this chapter. So what test would you use? Let's see if you can tell me. Okay, Pooja says homogeneity. What do y'all think?
The goodness of fit test.
Okay, I heard goodness of fit. Any other choices? Caledon? Okay, it turns out this is homogeneity. Pooja was right. Caledon's right too. Good, finally got it in there. Okay, and let's see why. Okay, well, goodness of fit means you have a known distribution and you're going to compare one single group to that known distribution. Do we have one single group here? We have two groups, right? We got men and we got women. And we don't know either's distribution. Does that make sense? So this is definitely going to be a test for homogeneity because we're comparing two different groups at which we don't know either's distribution. We want to find out if they're the same distribution as each other or not. Any questions on that? Okay. Again, what I've found is that's the most important thing, is to be able to answer a question, what type of test is it? Because if you can't do that, you don't even know how to start. Okay, how about this next one? Okay, let me read it. 70% of all Steller's jays nest in pine trees. 20% nest in aspen trees, and the rest nest in other places. A biologist has observed 250 Steller's jays that were given a special strength gene, okay, and then tagged to see if the distribution is different for Steller's jays with that gene. 201 of these tagged jays nested in pine trees, 39 nested in aspen trees, and the rest nested in other places. Conduct the appropriate hypothesis test. So again, my question to you is, what kind of test is this? And let's see if you can tell me. All three of you. Okay. Kaladin? Okay, so Pooja and Mike said good as a fit, and Kaladin says independent. Okay, this is good as a fit, and let's see why. So the idea is, if you read the first sentence, we know the population of good old regular jays. Okay, and by the way, if you don't know, Steller jays, that's our main bird in Tahoe. A lot of people think they're blue jays, but they're not. They're Steller's jays. And we know the population, the nesting population, for regular old Steller's jays. That's a known distribution. We have these genetically modified species, GMO jays, I call them, which we don't know about. So we're testing this don't know about distribution to a known distribution. And that's why it's a good as a fit. Caladon, does that make sense? Is that clear? So if you have two distributions you don't know and you're comparing, then it's a homogeneity. If you want to find out if one answer to another answer independent or not, that's test for independence. And sometimes you'll say related or independent, associated, a lot of words for independent. Okay, but this is definitely good as a fit. Any questions on that idea? Okay, let's do another one. I think I have one more if I remember right. Do I have one more? Yeah. This one we're actually going to do because it's worth it. Okay, does the number of months that transfer students take to transfer follow a normal distribution? Okay. Students take an average of 32 months to transfer, and the standard deviation is 4 months. The table below shows the number of months students take or took to transfer. Conduct the appropriate hypothesis test. Provide your interpretation. So what test is this? What do y'all think? Pooja thinks good as a fit. How about the two of you?
Oh no, this one's got me stumped.
Got you stumped? Okay. Caladon? Stumped as well. Okay, Pooja, you're not stumped. You got it. And that's nice to hear. Not nice to hear that two of you guys are stumped, but the idea here is we have this sample. We want to find out if it follows a normal distribution. Normal distribution is a known distribution. We know everything about that distribution. We could draw a picture. We know everything about it. So we have a single sample, and we want to find out if it fits the normal distribution. Does that make some sense? Does that unstump you?
So basically, if the distribution is known, or if we have an idea of what the distribution is, then it's a goodness of fit. If we don't know the distribution, then it's just the other chi-squared test.
Yeah, so if we have a known distribution and an unknown, and we want to find out if the unknown is the same as is the known, then that is goodness of fit. If we have two unknowns and we're comparing, that's homogeneity. Does that make sense?
Yes.
So that's the big difference. Okay, so now, again, we got a little time, so let's do this one. How do we come up with the expectance? Any thoughts? There is a way to do this, but it takes some work. I don't see y'all jumping in. Normal looks like this. The mean is 32. Okay, so Caledon says add them up to divide by 4, but that doesn't work because that would be if it was a uniform distribution. Does that make sense? So instead, this is a normal distribution, and we're comparing with normal. So now we have to use our normal stuff. So in particular, we have the mean was 32. Notice if you go to the left of 32, by the standard deviation, you get 28. And if you go one more standard deviation, you get 24. And then if you go right by 4, you get 36. And that's one standard deviation away. So it's been a while since we did these. That's why I want to do this one, because at least I can do this part of it. So just to continue on the picture, I am going to also go to the left by 4 from 32. That was 28. Just to show you what's going on. And let's go the right by 4 twice. And that was 40. Because that might help us, because then we can start using the empirical rule. So what we want is first less than 24. Well, that's the tail of 2 standard deviations. Remember that the inside is 95%, the outside is 5%, the tail is 2.5%, or 0.025. Any questions on that? Okay, similarly, we could do this tail over here. Now that's one standard deviation. Inside is 68%, so outside is 32%. So the right will be half of that, which is 16%, or 0.16. There's a good review from chapter 6. Okay, and then what's left is going to be 1 minus 0.16 minus 0.025. 1 minus 0.16 is 0.84. Minus 0.025 is 0.815. Any questions on how I got these three numbers? There's a lot of work here. It's all chapter 6. Okay, so now if we want to find the expected that's less than 24 months, what we can do is we can take the sample size, total sample size, if we add them up, 20 plus 60 is 80, plus 65 is 145, plus 39 is 184. I did my head right. So if I take 184 and I multiply it by 0.025, I get about 5. And that's going to be expected for the first item. Similarly, if I take, what was it, 184 and multiply by 0.815, I get 150. And that'll be the second item. Did I miss an item? 24 to 32. Oh, I did. Sorry about that. That's a total of 0.815, but we need to cut this into 2 pieces. And now we got to look at the pieces. Any questions? Let me ask you, you lost?
Kind of.
A bit lost? So this is a normal curve, okay? And the normal curve, another way of doing it if you want, is you could use your calculator and you could do a normal, normal CDF if you don't want to do what I did without using the calculator. How did I get this last number 5, Tricia? So which is the last number?
I'm sorry, my connection's really bad.
Okay. You said the last number. So do you mean 5? That's the last number I wrote.
I think I was asking how you got. No, I was wondering how you got the point. I think it was like 815.
Yeah, that was that whole area between 24 and 36. And then I remember we're actually cutting it into 2 pieces. So let me show you the easier way for you guys probably is to use your calculator. And for the 24 to 32, we could just do normal CDF. Okay, and hopefully you remember how to do normal CDF. Lower bound is 24, upper bound is 32. The mean was 32. And the standard deviation was 4. And I get about 0.477. And then you can do the same thing, but between 32 and 36. And what I get is 0.341. So then what you could do is you could take 0.477, multiply it by the total again. The total is 184. So 184 times 0.477 is 88. And that's the expected for 24 to 32. And then you do the same thing for 0.341. And 0.341 times 184, I get 63. I'm rounding to the nearest whole number. And then I could do the same thing with over 36, the 0.16. And when I put in 0.16, yeah, I get 29. Okay, and then I'm not going to do it because we've already done one like it. I just want to show you how you got these numbers. Now we have observed, we have our expected. We pop those into L1 and L2, use the GOF test, and that'll give you a p-value. Any questions at all on that idea? Okay, if there aren't any questions, I'm going to write down the secret word. And the secret word for the day is independent. Because one of our tests, our main tests, was a test for independence. And you got to have the word independent in there in H0. So that's pretty much what we need to talk about today. We've gone about an hour, 15 minutes. That's kind of around my goalish. So that's about the right amount of time. We only have 2 more webinars. You realize we're getting close. So that's just a note. So it's almost time to start thinking about the final. We're 3 weeks from the final. Okay, and I want to mention, since we're here, if you go to the modules, and you go to week 8, which is a midterm week, then you'll see midterm key. You know what? I hit the shell by mistake, or maybe I got the wrong link. I might need to fix this. Huh. Well, you will see midterm T. Right now it has the shell, but that'll be the key soon. Let me make it happen well.
It was in there earlier.
It was?
Yes.
How did it get undone?
Yeah, it was.
I don't get it. Okay, well, I'll fix it. I promise. So you've seen it?
Yes.
Did somebody sneak
Yes,
in
I
and
saw
get it out? Just kidding. I don't think you don't have the ability to do that. You don't have the password for that. Let me see something. Hmm? Well, I'll fix it, I guess. Sorry about that.
If you go down a little farther below the
Oh, there it is. Aha, there's my key. I don't know why I have another key that isn't the key. So there's the key. Oh, good, good. Okay, so it's all there. So again, you could look to see what you got wrong or you did it right. And if you if you don't remember what you did, if you send me an email, I can remind you on a particular problem. But it's there, and you know, again, you definitely want to get it if you didn't get it before, so that you do well in the final. Okay, not it's exactly the same problems, but some of the same things are going to happen again. So if there's any questions, I'll be happy to answer. And if not, we can say goodnight too. And I'll be checking the project discussion board to help you out on whether you have a good idea. Okay, good night, Colin.
Have a good night.
Have a good night, Mike. Any questions, Pooja? No, I guess not. Okay, well, if there's no questions, then I'll say good night to everyone. And thank you for watching this webinar, archived or live. And I'll see you next week.